we were doing pretty good here. We were just talking about the pH scale and about that time around time. But basically, we talked about how all these acids and lemon juice and so forth. In fact, this one even shows that hydrochloric acid can be concentrated to the -1. I don't know about that, but I have heard of those kind of things. But we'll just say it stops at 0. Battery acid and all this going to tomato. Notice the things we eat and drink tend to be on a little bit higher here. Things like lemon juice we tend to water down and dilute and add to other things first. But once you hit pure water, your blood is slightly basic, and then you have seawater, baking soda, soap, ammonia, hair remover, pretty strong, and so is oven cleaner. Oven cleaner is one of the more serious, at least strong bases that you can get your hand on. Bleach also. Not good for your system, either one. Now, bases, you notice, are used for cleaning supplies. Acids would be equally perhaps effective at eating away things, but they react with metals too much for faucets and pipes and stuff, we said. So anyhow, enough of that. Now, if we said acids and bases are kind of like opposites of each other, then the question is, what happens when you put opposites together? You'll hear the expression opposites attract. Is that what's going to happen? Well, not exactly. Let's look at an example real quickly and see what happens when we put those together. Let's start with hydrochloric acid. This is the same acid that's in our stomach. So HCl, all right, and this means, remember, hydrogen ions and chlorine anions, all right, plus sodium hydroxide. Basically, sodium hydroxide, obviously a base because it has a hydroxide, but it is also the biggest ingredient in Drano. Okay, so pretty nasty stuff. All right, what's going to happen when we add these two things together? Well, you think, oh, there's going to be a big bang and stuff, and really, actually, nothing happens. You take a clear liquid, hydrochloric acid, you mix it with a clear liquid, sodium hydroxide, and you pour them together and you get another clear liquid. But the clear liquid is different over here. Okay, now we know the positive part of one compound is going to swap with the other. This would be a double replacement reaction. Someone says, what is that? Well, don't worry, we'll get to that. But basically, they're going to trade partners here. The hydrogen, which is positive, needs a negative partner. It wants to get rid of the chlorine, so it's going to gain the OH. OH, or hydrogen hydroxide, plus the sodium has a positive. It needs to go with a negative, so it will pair up with the sodium chloride. So these kind of traded partners there. All right. Now, if we look at these, sodium chloride down here, we should notice, and that is salt. All right. And HOH, we said, is another name for water. So basically, we have salt water, which is still clear. So we had a clear thing plus a clear thing, but we have changed it drastically. Hydrochloric acid, especially, is very strong. This is what's in your stomach. It's what burns your throat on the way up when you throw up, and that's even after it's been mixed with food and whatever else. All right. So this is a base, which is strong enough to kill you if you were to ingest it. So very nasty stuff, cleans out your pipes. But you mix them together and you get basically salt water. All right. If you were to do this reaction and did it exactly the equal concentration so that they cancel each other out, you could actually gargle with this or even swallow a little bit of it and it would not hurt you. Now, I don't recommend you do that because if you didn't get exactly the same amount, there might be some hydrochloric acid left over or some sodium hydroxide, Drano-y type stuff left over, and you wouldn't want to do that. But theoretically, if you mix them together perfectly, you would end up with salt water and it would be fairly harmless. And interestingly enough, this is a very strong acid. This is a very strong base, and the resulting mixture would be completely neutral. All right, and so this is called, anytime you have acid plus a base, it's called a neutralization reaction. Okay, because you've added an acid plus a base, and you yield salt. I'm going to say a salt, not a salt. A salt is something that goes with battery. That's a salt and battery. That's a whole different thing. But a salt plus water. Okay? And so salt is neutral. In fact, the definition of a salt in chemistry is something that comes together from an acid and a base. There can be some salts that are still slightly acidic or slightly basic, but in general, salts tend to be neutral. Now, this particular one is table salt. You don't always get sodium chloride or table salt. You might have potassium chloride. Say we had done KOH, potassium hydroxide, then instead of sodium chloride, you would have got potassium. All right, chloride. So there's different kind of salts. All right, remember we talked about the halogens, the chlorides, the fluorides, and all those. Those make different kind of salts. There's also carbonates and sulfates and stuff. They're salts. Okay, plus water. Now, not every acid reaction will produce water, but most of them will include water. And it is also neutral. So this is neutral, so you've completely neutralized. If you add exactly the right amounts and the right strengths of acid and base together, they will neutralize each other, and you end up with a completely neutral products that are left over at the end. All right? Now, a lot of times in your body, it's very important that you have a particular pH and that you keep it within a certain boundaries. Your body's always trying to adjust things. Your blood needs to be between 7.3 pH to 7.45. If it gets too strong or too low, then you can have some serious problems and basically die, which is probably the most serious problem you can have, right? So it's in your body's best interest that your pH doesn't drastically go up or drastically go down. And it's also true when we're doing certain chemical reactions. They work best if they're in an acid solution or a basic solution. So we don't want them to change drastically. We want them to stay about the same. And to do that, we use what are called buffers. All right? Buffers, basically, are chemicals that can absorb, or release hydrogen ions or hydroxide ions to keep the pH from changing. Okay, so if your blood gets too acidic, for example, then it could give off hydroxides, and that would help bring up the pH to a more basic one. If it gets too basic, then it could release hydrogens, which would cancel it out and keep it about the same. This is important. For example, bufferin, salicylic acid or aspirin, was a great pain reliever. Unfortunately, it's acid, so if you throw that in your stomach, which is already filled with hydrochloric acid, it could cause you to have an acid upset stomach. So a lot of people said, well, can we come up with something? And the people from bufferin, all right, the aspirin bufferin, they said, let's put a coating on here. It's a buffer, and basically that buffer keeps the pH of your stomach from going up, even though you are absorbing salicylic acid, which is an acid, so it would make it a little more acidic. But there's some of the coating and other materials in there in the bufferin help to soak up some of the hydrogens so that it doesn't actually cause your stomach pH to go higher, giving you hydrochloric acid. Now, in your blood and your body, very often you use sodium carbonate, NaCO3, plus hydrogen. Okay, and it will form what we call sodium bicarbonate, which is basically baking soda. Okay, so if your body had too much acid, you had a bunch of these acids floating around, your body could release sodium carbonate, which would hook up with that and make sodium bicarbonate. On the other hand, if your blood started getting too high a pH, too basic, then it could release some of these hydrogens, and this reverse reaction can happen. So this is one of those reaction. It can go both directions. If it needs to, it can give the hydrogens back up to make your blood a little more acidic and less basic and bring it back into balance. And so constantly there's this change back and forth. Okay, interesting enough, we might also mention the CO3 that comes from here is manufactured from the carbon dioxide. So this also is related to your breathing and how much carbon dioxide you have in your blood, and that can affect how acidic your blood is. All right, so this is kind of a balance. This is a buffer. This is sodium carbonate and sodium bicarbonate are buffers that can either absorb hydrogens or release hydrogens to keep the pH of the blood about the same and keep you happy and healthy. All right. All right, let's just talk a little bit more about salts. Okay, salts, we said, tend to be neutral. Okay, and salts, when you put them in water, tend to dissociate. One S. There we go again. Associate, which is basically a fancy way of saying they separate and come apart. Okay, in water. And they form ions. All right. For example, if you put salt, which is a salt, if you put that in water, you would separate into sodium positive ions floating around and chlorine negative ions. And when we talked about water dissolving, salt dissolving, we talked about how those are attracted to each end of the polar molecule of water, and that's basically how they dissolve. Okay. You could have others, potassium chloride. Okay, positives, negatives, same thing. It would separate, and so on. So they do that. Now, when you have these ions floating around the water, these are also known as, so we could say that they form electrolytes. All right, you may have heard of electrolytes when you're drinking Gatorade. They're supposed to have sodium and potassium and some of these things. Supposedly that your body's just sweating out so badly that you need to go pay however much money to drink a sporting drink, which if you like the taste of it's fine, because that's about all you're getting out of it. You're probably, most people, unless you're just working out for 5 or 6 hours a day out in the hot sun, you're probably not going to need a whole Gatorade full of electrolytes, but sometimes you can get low on them. All right, and electrolytes are just ions that conduct electrical currents, or electricity basically, when they're in solution. We said water is neutral. It's also true if you have pure water, it will not conduct electricity. That does not mean you can sit in the bathtub and throw a transistor radio or something while it's plugged into it and not get electrocuted, because once again, as soon as you step in the water, if it was pure before, which it probably wasn't, probably had things dissolved in it already, it won't be by the time you get in there, because there's salts and stuff in your sweat and body is going to get in there and it's going to conduct electricity and it's going to kill you. But if you had perfectly pure water with nothing dissolved in it, it would not conduct electricity. But if you dissolve electrolytes or salts into it, then they will, these positive and negatively charged electrolytes will allow it to conduct electricity. All right. What are some examples of salts? All right, we already talked about sodium chloride. That's pretty common, just for the record. CN is cyanide, so this is sodium cyanide. All right, sodium cyanide. You may have heard of cyanide. This is poisonous, extremely poisonous, used in rat poisons and things like that. You may have KNO3. K is potassium. NO3 is nitrate, so potassium nitrate, we should have known that. Very important in fertilizer. It's also important in gunpowder. Ammonium nitrate, similar thing. Salt is used in a lot of the anhydrous ammonia and stuff that they put down in the ground for fertilizer by farmers and stuff. But it was used to make the bomb that took out the federal building in Oklahoma City quite a few years ago. But it can be fairly dangerous because that now it's regulated who gets a hold of it or not. Potassium chloride, we said, is basically salt substitute. A lot of times we talk about salt substitutes, and instead of sodium chloride, because we get so much sodium in our diet, you could use potassium chloride, a very, very common salt substitute. But once again, if you get too much of that, it can also be bad for you, just like regular salt. Calcium chloride, oops, put the L on the wrong side, sorry. Calcium chloride is very important as a de-icer. A lot of times they put, when they mix the different stuff they spray on the roads or scatter on the roads, a lot of those will have calcium chloride in it because it helps to de-ice things. And finally, but not least, sodium fluoride, which is what we have in our toothpaste. If you look on the ingredients, it'll have sodium chloride, and that's what helps protect your teeth. All right, we're almost finished. We're going to talk just a little bit more about some things, and then we will be done with acids and bases and ready to move on to types of reactions, the 5 main types that we're going to talk about.